Our speaker today is Saeed Hamoun, who will speak on the rational topological complexity of coformal elliptic spaces.
Okay, thank you, John, for giving me the word. First of all, I would like to thank the organizers for the invitation. I'm so glad to give a talk in this seminar. And I have to present myself first. My name is Saeed Hamoun. I'm a PhD student working on the rational topological complexity with my supervisors, Youssef Rami and Lucille van der Broek. So today I'm going to talk about topological complexity, which was introduced by Michael Farber in his approach to the motion planning problem. And more exactly, I'm going to talk about the rational topological complexity of coformal elliptic spaces. Before to begin, let me say a few words about our background. Fs is a topological space. The topological complexity of S, denoted by Tc of S, is least integer n, for which S times S can be covered by n plus 1 open subset U0 up till Un, and over HUI there exists a continuous local section of the evaluation mean. While Lusternick's normal category of S, denoted by cut of S, is least integer n such that S can be covered by n plus 1 open subsets U0 up till Un, each of which is contractible NS. Note that the TC and cut are about homotopy invariant. And now the one may wonder what's the relation between these two homotopy invariants. For instance, let's point out to this inequality, which is that topological complexity lies between cut and 2 times cut. But there exist some spaces for which these two extremum may be reached. In particular, for the sphere Sn, we have Tc of Sn coincides with the category of Sn, which is exactly 1. Fn is odd, while Fn is even. Topological complexity of Sn equals 2 times category of Sn, which is exactly 2. Moreover, for the sphere Sn, the topological complexity coincides with the 0 divisor couplant of Sn. And here we consider the 0 divisor couplant over Q, which is the maximal length of a non-trivial product in the kernel of multiplication over the rational cohomology. More precisely, for the sphere Sn, we have the rational cohomology is given by the quotient algebra, given by the polynomial algebra Q of x over the ideal generated by x to the power 2, where x is an element of degree n. And here, if you consider this element x tensor 1 minus 1 tensor x, which is an element in the kernel of the multiplication over the algebra of the cohomology, this element satisfies x tensor 1 minus 1 tensor x to the power 2 equals 0 if the degree of x is odd, and it is different from 0 if the degree of x is even. That means that the 0 divisor couplant of Sn equals 1 if x is odd, and it is 2 if degree of x is even. In the sequel, all topological spaces are supposed to be simply connected CW complexes of finite type. And I recall that the rational topological complexity of a topological space S and the rational Ellis category of S are defined by TC0 of S is the usual topological complexity of S0, and the rational LS category of S is the usual LS category of S0, where S0 here is the rationalization of S. That means that S0 means is the rationalization of S, means that the homotopy of S0, or equivalently the cohomology of S0 over Z, are rational vector spaces. And if there exists a map for S from S to S0, which induces a quasi-isomorphism from the rational homotopy to the homotopy of rationalization, and also an isomorphism from the cohomology of rationalization to the rational cohomology. And here, note that the rational topological complexity lies between zero divisor couplet of S and the usual topological complexity. And we note that the rational versions of the homotopy invariant TC and CAT satisfies the same inequality satisfied by the usual case. And we have TC0 lies between CAT0 and 2 times CAT0. Our general goal is to study the rational topological complexity in terms of rational LS category for elliptic spaces. And we say that a topological space S is elliptic if the rational cohomology and the rational homotopy are both finite dimensional. In this context, or in this framework, our main tools are the Sullivan models. And we say that lambda VD is a Sullivan model for the topological space S if lambda VD is a commutative Cauchy algebra whose cohomology is exactly the rational cohomology of S. And here, lambda V represents the free commutative algebra generated by the vector space V. If in addition, we say that lambda V is minimal if the differential is decomposable. And in this case, we have V is quasi-isomorphic to the rational homotopy. As examples of minimal Sullivan model, we have for the sphere, we have the rational cohomology of the sphere is given by Q of X over X to the power 2. I mean the ideal generated by X to the power 2, where X is an element of the degree N. Then in this case, we have lambda VD equals lambda X F with the differential 0 if N is odd. And in this case, we have X to the power 2 equals 0, which means that the algebra lambda X is an exterior algebra. While if N is even, we have lambda VD is given by lambda XY, where X is a cocycle and the differential of Y is the square of X. And here, note that all the powers of X are existing and Y is introduced to kill X to the power 2. The same thing is for projective space CPN, and we have the rational cohomology of CPN equals the Cauchy algebra given by the polynomial algebra Q of X over the ideal generated by X to the power N plus 1. And here we have its Sullivan model is given by lambda XY, where X is a cocycle of degree 2, and the differential of Y is X to the power N plus 1. The last example is an example so important for our study. It is about the homogeneous space SU6 over SU3 times SU3, whose Sullivan model is given by lambda x1, x2, y1, y2, z, where x1 and x2 are 2 cocycles of degree respectively 4 and 6. And the differential of y1 is the square of x1, the differential of y2 is the square of x2, and the differential of z is x1 times x2. And note here that the degree of y1 is 7, and the degree of y2 is 11, because the differential t is increasing the degree by 1. And moreover, the rational cohomology of this space is given by the cohomology classes x1, which is of degree 4, x2, which is of degree 6, and x1z minus x2y1, which is of degree 13, x2z minus x1y2, which is of degree 15, and the last one represents the top class of the space, which is given by x1, x2, z minus x1 to the power 2, y2, which is of degree 19. And note that for all these spaces considered here are all elliptic, because their rational cohomology is finite, as you can see, and also the rational homotopy corresponds to finite dimensional vector space. In this work, we are interested in studying pure minimal Sullivan models, and we say that lambda VD is pure if all generators of even degree are of differential 0, and the differential of generators of odd degree are polynomial in generators of even degree. And we say that a topological space S is formal if its Sullivan minimal model lambda VD is quasi-isomorphic to its rational cohomology with differential 0. And as example of formal spaces, we can find the sphere Sn and the projective space Cpn are about formal, while the homogeneous space considered before is not formal. For the rational topological complexity of formal spaces, which is relatively simple, Lechuga and Morio proved that for any formal space, the rational topological complexity coincides with the zero divisor coupling of the topological space. And as I said before, we wanted to study or to express the rational topological complexity in terms of rational Ellis category. And we found out that we need another classical number, which is the homotopy characteristic. And for S elliptic, the homotopy characteristic is defined to be by dimension of the even part of the rational homotopy minus the dimension of the odd part of the rational homotopy. And in this case, by ellipticity, it is known that Kp is always negative, and if chi pi of S equals 0, then in this case, the space is formal and it is called F0 space. If moreover, lambda VD is a minimal model of the topological space S, then we have chi pi of S is the dimension of the even V even minus the dimension of V odd, and we can denote it by chi pi of lambda V. And here in our first result, we prove that in particular, for any pure coformal elliptic space S, the rational topological complexity of S can be expressed in terms of rational Ellis category by the equality TC0 of S equals 2 times category of S plus chi pi of S. And here I wanted to recall a result due to Gisuk-Morio-Parent, which relates the rational topological complexity to a rational Ellis category in a particular case where S is elliptic and the rational homotopy is concentrated in odd degree. And in this case, we have TC is exactly coincides with the rational Ellis category, which is the dimension of the odd part of the rational homotopy. In this theorem, the space may be non-formal and not necessarily pure. And it's worth also to note that under the same condition of this theorem, TC0 of S can be expressed in terms of rational Ellis category, and we have TC equals 2 times category plus chi pi. In fact, here, 2 cut 0 of S is 2 times the dimension of P odd, and chi pi equals minus the dimension of P odd. And we have 2 times cut plus chi pi equals 2 times dimension of P odd minus dimension of P odd, which gives the dimension of P odd, which is exactly TC0 of S. In order to prove the previous result, Jisoo, Murillo, and Parent used an approach in the same spirit of the rational Ellis category characterization due to Felix Halperin. More exactly, if lambda v d is a Sullivan model for S, and if mu lambda v is the multiplication over the algebra lambda v, and if considering rho m is the projection from the algebra lambda v tensor lambda v to the quotient algebra lambda v tensor lambda v over the ideal generated by over the ideal kernel of mu lambda v to the power m plus 1. Here, the differential d bar is the differential deduced by t. Jisoo, Murillo, Parent proved in 2012 that TC0 of S is less or equals than M if rho m admits a homotopy retraction. And then they conjectured that TC0 of S is exactly the least integer m for which rho m admits a homotopy retraction. And the result turned out to be true by the theorem of Karaskel, who proves that TC0 of S is the least integer m for which rho m admits a homotopy retraction. Here, note that the kernel of mu lambda v is an ideal in the algebra lambda v tensor lambda v, which is generated by the element of the form v tensor 1 minus 1 tensor v. And here, to alleviate the heavy expression, we identify v tensor 1 to v, and we identify 1 tensor v to v prime for v an element in the vector space v. Here, note that to prove that rho m admits a homotopy retraction, it is not easy at all. But if the homotopy retraction exists, then rho m is injective in cohomology. This fact induces another homotopy invariant denoted HTC of S, which is defined to be the least integer m for which rho m is injective in cohomology. And here we have HTC lies between the zero divisor cap length of S and the rational Ellis category of S. Moreover, if lambda v d is a Sullivan model for topological space S, then we may use the notation TC of lambda v, HTC of lambda v, cut of lambda v instead of TC0 of S, HTC of S, and cut 0 of S. And in the non-formal case, there exist some examples for which the rational topological complexity may be strictly greater than zero divisor cap length. And the first example was given by Fernandez Suarez, Guillen, Kahl, and Lucille van den Broek through a lower bound of the rational topological complexity denoted by MTC. And here I want to point out that MTC is defined by the fiber John. And we will see this example here by using the rational topological complexity characterization. It is about a non-elliptic space S with the zero divisor cap length equals 2, and whose minimal model is given by lambda v1, v2, z tensor lambda u, where v1 and v2 are two cocycles of degree 3, and z is of differential given by the product of v1 times v2, and u is a vector subspace generated by elements of degree greater or equals than 10. And here we consider the element v1 minus v1 prime times v2 minus v2 prime times z minus z prime. Here I would like to remind you that v1 here is identified to v1 tensor 1, and v1 prime is identified to 1 times v1, which means that this element here is in the kernel of mu lambda v to the power 3. And we can check that his cohomology class is non-trivial. Then we have here an element which is a cocycle in the kernel of mu lambda v to the power 3 with non-trivial cohomology class in this algebra here. But in the other algebra here, it is 0, which means that root 2 or this projection, which is root 2, is not injective in cohomology. And then we consequently have HTC of lambda v is greater or equals than 3, which means that TC0 of S is greater or equals than 3, which is strictly greater than 0 divisor cap length of S, which is here 2. As I said before, this example is important for us, and we will see here that the rational topological complexity of S is greater or equals than 5. We first consider the element x1 minus x1 prime, x2 minus x2 prime times z minus z prime, which is an element in the kernel of mu lambda v to the power 3, but which is not a cocycle. But by adding this part here in the right, we construct the cocycle omega, which is also in the kernel of mu lambda v to the power 3, and we can check that omega is of cohomology class non-trivial. And this by using quasi-isomorphism phi, which transform the algebra lambda v to the algebra A, which is more smaller and more simple to deal with. And here, the rational cohomology of the algebra A is given by the classes x1, x2, x1z, x2z, and the last one is the top class of the algebra A, which is x1, x2z. Here, our idea is to construct the maximal cocycle, the maximal number of cocycle in the kernel of mu lambda v in such a way that their product with cocycle omega is non-trivial. And for this example, in particular, we construct beta 1, which is x2 minus x2 prime, and beta 2 given by this expression. And we can check through quasi-isomorphism phi that phi tensor phi of the product of omega by beta 1 by beta 2 represents exactly or up to a scalar the top class of A tensor A. which means that omega beta 1 beta 2 is an element in the kernel of mu lambda v to the power 5, and whose cohomology class is non-trivial. It follows that the rational topological complexity of this space is greater or equals than 5. And note here that the rational LS category of this space is the dimension of the odd part of the rational homotopy, because here it is quadratic, and which is 3. And here, note that this 5 here equals 3 plus 2. 3 is the number which comes from the rational LS category, and the 2 is it comes from the length of beta 1, beta 2 in the kernel of mu lambda v, and that is the result that we want to generalize it. And here we will see a lower bound of the rational topological complexity for coformal elliptic spaces. And we say that as a minimal Sullivan model on the VD is coformal, if the differential D is quadratic, that is, D of V is included in lambda 2 of V. And here I want to recall the well-known results due to Felix Harperin for elliptic coformal spaces, which is, in this case, the rational LS category is given by the dimension of the odd part of the rational homotopy, which coincides with dimension of V odd. And after developing the technique that we saw in the previous example, we prove in particular that for any pure elliptic coformal model on the VD, and for any basis B of Vn, the rational topological complexity is greater or equals than the rational LS category plus L of lambda VB, or equivalently, the rational topological complexity is greater or equals than the dimension of V odd plus L, where L here is a certain couplant that we will describe next. To make ideas more clear about the couplant L, if we consider a Sullivan model on the VD, which is pure and coformal, and F and elliptic also, and Fx is Vn and Y equals V odd, and Fb is a basis of X. What we do here, the first thing that we do is to extend the Sullivan model lambda V to lambda W by associating to Hxi an element Ui satisfying the differential of Ui is the square of Xi. And here, as the differential D is quadratic, then it splits into operators of into the big graded operators dpq of this form, and because it is quadratic, then it increases the length of the even part by 2, and it decreases the length of the odd part by -1. And then D induces a degradation on the cohomology EH of lambda W given by each PQ. Here P corresponds to the length of the even part, and Q corresponds the length of the odd part. And our L is defined to be the maximal non-trivial product in H odd star of lambda W. Here odd means that length in the even part must be odd, but the second gradation is we don't care about it. As an example of application of this result, we consider the previous homogeneous space whose minimal model is given by lambda x1, x2, y1, y2, z, where the differential of x1 is 0, differential of x2 is 0, the differential of y1 is the square of x1, the differential of y2 is the square of x2, and the differential of z is given by the product x1, x2. We extend the lambda v to lambda w by adding the elements u1 and u2. The differential of u1 is x1 to the power 2. The differential of u2 is the square of x2. Here, remark that the element alpha, which is x2, and the element alpha 2, which is x1z minus x2y1, are two cocycles in H1 star. This one here, it corresponds to the length of alpha 1 in the even degree. And here we have 1. And for alpha 2, we have also 1 because the length of the even part is 1 here. And we can check that product of the cohomology classes alpha 1 by alpha 2 is different from 0, which means that L is greater or equal than 2. And actually, we can check that it is exactly 2. In this example here, we will see that the length L depends on the choice of the basis B. And we consider this example whose minimal model is given by lambda xi, yi, z, where xi are cycles and the differential of yi is xi to the power 2 for all I lies between 1 and 4, and the differential of z is x1, x2 plus x3, x4. For the basis B, we saw that L is 2 here. And we prove that by a changing of variables, we can construct another basis B bar for which L is exactly 4. Here in this paragraph, we will see an upper bound of the rational topological complexity for certain pure elliptic spaces. And our first general result here is that for any minimal Sullivan model on the VD, if lambda V tensor lambda U is an extension of lambda V D, where U is a vector space concentrated in odd degree, such that D of U is including in lambda V, then the rational topological complexity of lambda V tensor lambda U is less or equals than the rational topological complexity of lambda V plus dimension of U. And for lambda V, the pure elliptic minimal Sullivan model, if there exists a subalgebra lambda Z, which is F0 and satisfying Z even equal V even, and if in addition there exists an integer K such that differential D is homogeneous of rank K, then we have TC of lambda V is less or equals than 2 times category plus chi pi of lambda V. In this result, we have used the previous result and this result, which is due to Liu and also to lepton, which says that for lambda V D, a minimal Sullivan model, which is elliptic, if the differential D is homogeneous of rank K, then the rational Ls category is given by n times K minus 2 plus m, where n is the dimension of V even and m is the dimension of V odd. In the particular case where K equals 2, which corresponds to the coformal case, given an extension of before, then this upper bound corresponds to the dimension of V. And as an example of application of this result, we will consider also the homogeneous space of before. And here, let's consider lambda Z to be lambda x1, x2, y1, y2. Here we have the differential of y1 is the square of x1, differential of y2 is the square of x2, which means that this subalgebra is elliptic. And we have the number of generators of even degree is as much as the number of generators of odd degree, which means that lambda Z is an F0 model. And then we can apply the previous result. And here we have chi pi of lambda V is 2 minus 3, which gives minus 1. And the rational Ellis category of lambda V is exactly the dimension of the odd, because here the differential is quadratic, which is 3. Then by the previous results, TC is less or equals than 2 times 3 minus 1, which gives exactly 5. And as we saw that TC is greater or equals than 5, then TC it is exactly 5. Finally, here we have a complete result for this family, which generalizes the example seen before, and we prove that for any Sullivan model, which is elliptic and pure coformal of this form, lambda xi ui y, where xi are cocycles and differential of each ui is the square of xi. Then we have the rational topological complexity is given in terms of rational Ellis category by the equality TC equals 2 times cut plus chi pi, which is here exactly the dimension of V. For the first inequality, it holds by considering this extension, and here we take lambda Z to be the algebra lambda xi ui, which is here F0, because it is elliptic, and we have the number of generators of even degree is as much as the number of generators of odd degree. Then we can apply the theorem of the upper bound, and here we get TC of lambda V is equal less or equal than 2 times category plus chi pi. Category here is the dimension of VO, which is n plus 1, and chi pi is the dimension of V even minus the dimension of V odd, which is n minus n plus 1, which is minus 1. Then here it corresponds exactly to 2n plus 1, which is the dimension of V. For the other inequality, and as a total, we will consider the isomorphism phi from lambda V to A. And we prove that there exists a cocycle omega in the kernel of mu lambda V to the power n plus 1. And here I want just to say that this omega here is the same omega served in the proof of the theorem of the lower bound that we saw previously. And in this case, instead of considering the length L, we construct in an explicit manner the expression of a cocycle beta, which is in the kernel of mu lambda V to the power n, and satisfying its product by omega represents the top class of lambda V tensor lambda V. And we can prove this by using quasi-isomorphism phi tensor phi. And finally, we have each GC of lambda V is greater or equal than 2 times n plus 1, because omega, the product of omega by beta, lies in the kernel of mu on the v to the power n, which corresponds to omega, plus the n plus 1, which is the length of omega. That gives Tc of lambda v is greater or equals than 2 times n plus 1, and then it is exactly 2n plus 1, which is the dimension of v. As the work in progress, we are investigating in the calculation and the properties of the couplant L. And we want also to extend the obtained results to other classes of elliptic spaces. Here you find some of the references that we have used in this work. And for more details about this work, you have our article here, which is entitled On the Rational Topological Complexity of Coformal Elliptic Spaces. That was what I wanted to share with you, ladies and gentlemen, and thank you for your attention. If you have any question, I would be glad to respond. Thank you.
Thank you, Saeed.
Thank you.
I have a question, actually.
Yes.
Can any of these results be extended to higher TC? Have you thought about that?
For the higher TC?
Yeah.
Actually, we didn't think about the higher TC. What we are trying to do is at first step, to generalize this results to the spaces for differential is homogeneous of rank K, and we are trying to calculate this couplant L, and if it is okay, maybe we are going to see if it is generalizable to the higher TC.
Yeah, I think that would be interesting to see if there's something like the higher R, or let's say n TC of X is less than or equal to n times the rational category plus the homotopy Euler characteristic, something like that. Any other questions?
Can I ask a question?
Yes.
Yes.
Yeah, it's a very nice talk. Thank you.
Thank you.
So the rational TC is a lower bound for the ordinary integral TC.
Yes.
And in the case of, in your example with the special unitary groups, you found that the rational TC was 5. I just wondered if that lower bound of 5 is better than you can do by using the lower bound of 5 for the integral TC for that example is better than you can do by using ordinary cohomology. Did you check?
Here for the homogeneous space?
Yeah. So your rational TC is 5, so that means that
yes.
your TC is at least 5. But I wondered if that is an improvement on what you can do with ordinary cohomology and zero divisors.
By the zero divisor. The zero divisor for this space is 3.
Okay, right.
It gives a lower bound, but it doesn't give the exact value of the rational topological complexity.
Mm-hmm.
That's for what we have introduced this L to give the exact value for this TC.
Mm-hmm. Yeah, thank you.
And thank you for your question.
And I have one other question. You know, there's a spectral sequence. I'm forgetting a little bit, but it begins with the pure model and it goes to the actual model and you get information that way. Is there any way to go from your results that require pureness of the model to non-pureness?
Yes, I think that's here. Here in the definition of L, here in the definition of L, as you can see here, the differential D induces a degradation on the cohomology. It's maybe that we can. It's maybe that we can ask questions if we can associate to this degradation spectral sequence and try if there is any possibility to extend some results. But honestly, we didn't check.
Okay, any other questions? If not, I'll stop the recording and then people can still ask questions.